The goal of this video is to get you thinking about Antarctic geography a little bit. Antarctica is a very unique and interesting place. It's about 1.5 times the size of the US, which means it's very heterogeneous over space. You can't just think of it as one solid block of ice, but really it's a continent. And with that comes all the variability that comes with any continent at Earth's surface. So, for this video, as I said, we're going to think about Antarctica in that scale. This map, I think, helps illustrate the relative positioning of components of the Antarctic ice sheet and the rest of the planet. I think that this is really useful, especially when you start to think about where the permanent bases are that the United States Antarctic Program and other global Antarctic programs operate from. So you can see that we have our southern hemisphere continents. This is Africa here, South Africa. Here's South America. Here's Australia and New Zealand. And they ring Antarctica, which sits at the bottom of the planet. We often divide the Antarctic ice sheet into two halves, split by the prime meridian. And they don't exactly fall along these boundaries, but it's useful to see that half of the Antarctic ice sheet falls in the eastern hemisphere, east of the prime meridian, and half falls in the western hemisphere. And as a result, we refer to the side on the right of this plot as East Antarctica and the side on the left of this plot as West Antarctica. Of course, when you're at the South Pole, all directions are north. So understanding south, north, east, west can be kind of complicated. In this case, west is counterclockwise when we're thinking about going around Antarctica. East is clockwise. So this point would be east of that point, for example. The United States has 3 permanent stations in Antarctica. One, and the largest, sits right here, right at the edge of the Ross Ice Shelf, and this is called McMurdo Station. Most of the ground operations in Antarctica are dispatched through McMurdo as part of the US program. So to get to McMurdo, you fly to New Zealand. You fly from Christchurch, New Zealand to McMurdo. There's a permanent base at the South Pole itself, Amundsen Scott Base. That is a station where you deploy if you're going maybe up on the Antarctic Plateau, for example, which is in East Antarctica. There's also a permanent station here in this location we call the Antarctic Peninsula. This is Palmer Station, and folks usually get there to and from South America. So, as I said before, we have the West Antarctic ice sheet, which is that mass there. We have the East Antarctic ice sheet, which is this mass here, and then the Antarctic Peninsula. 3 common divisions that exist when we're talking about the geography of Antarctica. This plot is showing you the flow speed as observed from space of the ice on the Antarctic ice sheet. And we can see that the ice doesn't flow kind of uniformly slow to uniformly fast as you get out to the coast. Ice is routed through these narrow rivers of ice that we call ice streams. And there are a couple things plotted on here that can help build up some context for what we're looking at. This black line that goes all the way around here, around the continent, that is the grounding line. That represents the transition from grounded to floating ice. And so you can see Antarctica's major ice shelves as these very fast-flowing things that sit outboard of the grounding line. The color scale is saturated. The ice shelves are flowing actually on the order of 1 kilometer per year as opposed to 100 meters per year. But here we have the 3 main Antarctic ice shelves: the Ross Ice Shelf, the Filchner-Ronne Ice Shelf, and the Amory Ice Shelf. There are many others. You can see, for example, this is the Larsen Sea up here in the Antarctic Peninsula. We have the ice shelves that ring the continent wherever we have these fast-flowing outlet glaciers. Let me zoom in here for a second. You can see that there are a number of ice streams that feed the Ross Ice Shelf. These were historically called ice streams A, B, C, D, and E. They've now been given names after glaciologists who have done research in these areas. This collection of ice streams that feed into the Ross ice shelf, we call that the Sipal Coast. So on one side, the Ross ice shelf is bounded by the Sipal Coast ice streams. On the other side, over through here, let me use a different color actually, we have a really high relief mountain range called the Transantarctic Mountains. These kind of connect up through the Antarctic Peninsula and are the large-scale division between the East and West Antarctic ice sheets. As you'll learn, the Antarctic ice sheet is really responding to complex changes in the ocean. Oh, that's interesting. It's not letting me erase this. Let's try that one more time. The eraser's not working. That's okay. So the Antarctic ice sheet is responding to changes in the ocean, and so one thing that's really important is that we be able to differentiate the different ocean basins that contribute to changes in Antarctica. I'm going to close this PowerPoint for 1 second and bring it back up since it wasn't letting me zoom. There we go. Okay, so just like we have the Ross ice shelf down there at the bottom, this is the Ross Sea, this ocean basin over here. There's not a lot happening right now in the Ross Sea. Where most of the action is in Antarctica is the parts of the ice sheet adjacent to this region we call the Amundsen Sea. The Amundsen Sea has experienced significant changes over the last few decades associated with changes in the winds. As changes in the winds change pumping to the ocean, this pumping that drives the upwelling of warm water, what we've seen is that this warm, deep ocean water has made its way up adjacent to the Antarctic ice sheet in the Amundsen Sea. So the areas that are losing ice the fastest happen to be these glaciers that drain into the Amundsen Sea. This glacier right here, called Thwaites Glacier, and this glacier right here, called Pine Island Glacier. A lot of my research focuses on West Antarctica, Thwaites and Pine Island Glacier, and the Sipal Coast. So I wanted to give you some sense for that geography here. If we strip away the ice and we look at the elevation of the rock underneath, we get a map that looks like this. And we can see that East Antarctica and West Antarctica look quite different. East Antarctica, the bedrock sits mostly above sea level. So that color scheme, it transitions from blue to green, with that transition occurring at 0 meters above sea level. East Antarctica is largely cratonic continental crust. It's separated from the southern hemisphere supercontinent Gondwanaland and resulted in the large stable part of Antarctica. Most of the ice in the East Antarctic ice sheet sits on rock that's above sea level, and that makes it an intrinsically more stable glacier system. So this is where most of the mass is in Antarctica, 50-some meters of sea level equivalent of ice. And that ice is quite stable in response to modern climate change. By comparison, the West Antarctic ice sheet sits in this deep marine basin, primarily tectonic in origin. So there was an active rift system in West Antarctica, which we call the West Antarctic Rift System, that led to relatively thin crust that thermally subsided, leading to this relatively open marine basin. The ice sheet in West Antarctica, because it sits on the seafloor, and because that seafloor gets deeper and deeper as you get further and further into the ice sheet itself, that's quite an unstable system, naturally. We'll talk about that instability more in another video. But it's important to remember that West Antarctica is rapidly changing, sits in a deep marine basin, and as a result we call it a marine ice sheet. East Antarctica, not changing a whole lot because it sits on this high elevation cratonic crust. Finally, I think it's useful to think about the geometry of the surface of the ice sheet. West Antarctica is at low elevation compared to East Antarctica, which is quite large and quite high elevation. And we often subdivide East Antarctica into what we call domes. Regions that have a local maximum elevation. Those domes got called Dome F, Dome A, Dome C. This is Dome F or Dome Fuji. This is Dome A. This is Dome C. Many of our longest climate records that we've collected from ice cores exist from ice cores drilled exactly at these domes. This map here on the right, this is a map of every ice core that's been drilled in Antarctica. West Antarctica is a much younger ice sheet, more dynamic ice sheet. A lot of the US research is focused there. A lot of the European, Australian, other research groups, the Japanese, now more recently the Chinese, has been focused in East Antarctica. But the structure of the surface elevation tells us something about kind of the flow regime in these slow interior sites. And we use a lot of that surface elevation information to inform our selection when we're doing ice core science. Okay, that gives you a somewhat broad overview of Antarctic geography. From here, we're going to dive into some of the details of how these glacier systems work.